Okay, so welcome everybody. Today's last speaker is Mohammad Asif Elahi from NISER, India, from Bhubaneswar, and he's going to talk about observing the 21 centimeter line from the epoch of reionization. So maybe I'll send you a reminder when 5 minutes are left.
Sorry, should I start?
Yes, please.
Okay. Yeah. You said that you sent me a reminder before 5 minutes. Okay. I couldn't follow
Yeah.
that. So can you confirm that you can see my cursor?
Yes.
The
So
point.
we can see the cursor, we can see the
Oh,
screen.
fine. So yeah, thanks very much for having me in this wonderful seminar series. So most of the work has been done from Indian Institute of Technology, Madras, but currently I am a postdoctoral fellow at NISER. So let's start. So the topic is the observing the 21 centimeter line from an interesting epoch in cosmology, the epoch of reionization. So I sense that the audience is slightly off from this line of work. So I'll try to be a little bit explanatory in the sense, but yeah, but some of things will be very technical, and I'll appreciate if you can directly ask the questions if you cannot follow those technical parts. So the epoch of reionization is the topic that I'm going to talk about. So it is an interesting epoch when it's just when the radiation decoupled from matter, and the radiation that we currently see as CMB, it is that epoch when the radiation decoupled from matter. The universe was mostly filled with neutral hydrogen. And the epoch of reionization, it starts when the first stars and galaxies start to form, and they start to ionize the neutral hydrogen. So this is the second ionization, the reionization of the neutral hydrogen in the universe. First being the pre-recombination era, when things were already ionized. So this is an interesting epoch. There are several unknowns in this epoch, and there are very few direct probes. So I'll point out some of the unknowns. For example, we are not sure when exactly did this happen. I mean, when the first stars and galaxies formed, this particular line, and it is mostly the most theoretical constraints are tell that it is roughly around z equal to 30, but that is not confirmed yet. And what was the nature of the reionization? I mean, what are the sources? Which sources caused the ionization? And then there are specific questions. For example, as the ionization started to grow, how did the ionized bubble grow and the merge? Was it patchy? Was it uniform? What was the size of the bubble at different redshifts? For example, what was the shape? Was the bispectral? Was there a non? There is a non-Gaussianity. How much is that? These kind of questions. Then there are a question about thermal history. The X-ray and the Lyman alpha, how did they couple and they heat the intergalactic medium? And there are newer studies which says that can it constrain dark matter using their effects on the reionization parameters, for example, the mean temperature of the reionization or the power spectrum of the 21 centimeter signal. And then there are new observations, for example, instruments such as EDGES or JWST, which tend to shake most of the theoretical model that we have. And then so there are, as I said, that there are several unknowns. Most of the theoretical models are still open, and there are few direct probes. One of the direct probes is the 21 centimeter line. So what is this line? So this line originates from the ground state of neutral hydrogen, which has two hyperfine levels, and their gap is in units of frequency, their gap is 1420 megahertz, some 6 electron volt. And in units of wavelength, this is 21 centimeters. That's how the name comes. The interesting thing is that this rest frame frequency 1420 megahertz, it gets redshifted due to the cosmological redshift. And by observing the signal at some different frequency, we can probe the universe, where the origin of the signal at some redshift. For example, we can directly observe the EOR by tracing this line, which is coming redshifted from a redshift of 8, for example. To see this signal, we have to just tune our instrument to a frequency 150 megahertz. So if we tune our instrument which in our case is a radio interferometer. I will talk about that more. If we can tune our instrument to certain frequency, which is very easy, then we can get information from the redshift by observing this line emission signal. What I am mostly concerned, what I am mostly concerned is the brightness, is something called the brightness temperature fluctuation of the signal. So what is this? This is a lot of complex physics goes into measuring the brightness temperature fluctuations. For example, I will not go into the detailed physics of it because the time wouldn't permit me to go. But there is a temperature that corresponds to the 20 centimeter signal. It is called the spin temperature. And the difference between the spin temperature and the CMB temperature is what I am basically trying to measure. This is called the brightness temperature fluctuation. So the fluctuations against the mean is what is my more interest. And the neutral hydrogen fraction, the matter fluctuations, and also redshift space distortion, line of sight effects, all these cosmological things goes into this measurement. And there are several papers on this subject. And this is a rich subject. So this is around 3 decades now, almost 3 decades that these people are trying to measure the signal, but the signal is not yet measured. I work on a specific class of this signal where my interest is not in modeling the mean or individual or making an image of this kind of signal, but rather measuring the power spectrum of the signal. So basically, what is it? So I want to measure what scale, how much power is there. So if I can, for example, measure, so this is basically a quantification of the variance of the fluctuations at different length scale. This is called the power spectrum. So if I can measure the 20 centimeter power spectrum, what I shall get? So here is an example. So this is a simulated data. In these simulations, people have simulated the epoch of reionization. What is it? So for example, you can see, so this simulation goes in this clockwise fashion. So for example, these are red dots. You can see these are the very fast stars and galaxies, for example. And these stars and galaxies, they start to ionize the universe, you can see as some gaps in these maps. The gaps starts to grow. For example, here the gap is bigger, and then as we progress in time or in redshift, the entire universe become completely ionized. So this picture, it directly translates into the power spectrum. So by checking which scale has how much power, we can directly quantify how much neutral fraction the universe had, at what redshift, etc., etc. So if we can measure the radiosimeter signal, we expect to see this kind of measurements, in terms of the power spectrum. The amplitude of the signal is expected to be roughly, if our theoretical estimates are correct, then the expectation is roughly around 100 to 10 to 100 millikelvin square. So what I tried to say in this first few slides is that EOR is scientifically interesting. There is a lot of things that we can model, but there is not enough good probes. And the 20 centimeter can signal from the neutral hydrogen, as it comes to us redshifted, it can probe this effort. So my goal is to measure this. So I will not go into much details, but let me introduce you to some of these instruments that are currently working worldwide. One of the instruments is the GMRT, which is in India. So there is one instrument in Australia, which is called Murchison Wide Field Array. And my next few slides will be covering only this instrument because this is mostly what I focus on. But there are other instruments, for example, the Hydrogen Epoch of Reionization Array, HERA, in short. This is in South Africa. There is a telescope LOFAR, and the Square Kilometer Array, you probably have heard the name of. This is an international project currently being built in South Africa and Australia. So also one of the major goals of all these instruments is to measure this 21 centimeter power spectrum from the epoch of reionization. So as I said, that the instrument that I'm currently working on is the Murchison Wide Field Array. This 4x4 dipoles form one tile, or what we call an antenna. And then there are multiple such antennas which form an array. How does this array measure the 21 centimeter signal? So this is how it does. So it basically measures the Fourier transform of the sky. So this short separation, which is called the baseline. So these are some radio astronomical terms, but yeah, so I have to use those terms to explain these things to you. So the short separations or short baselines probe the large scales, whereas the large baselines or the large separation probe the small scale features. So this instrument, by its design, probes the different scales of the 20 centimeter 3D maps. And this instrument operates in a frequency dependent way. The different frequency probes the line of sight Fourier modes. So together it probes the 3D power spectrum. This is the angular power spectrum, angular wave numbers, and these are the line of sight wave numbers. So if we can measure this 3D 20 centimeter brightness temperature cube, we expect to get a power spectrum like this. But for practical purposes, the power spectra is plotted in the angular direction in this way and line of sight direction in this way. Why? This will be very clear soon. These are already well known in 20 centimeter cosmology groups. But I checked the audience that I should explain these things to get a proper sense of what we are doing. So one of the main challenge in observing the 20 centimeter signal, and why it has not been observed yet, is the foregrounds. So as I said previously, the 20 centimeter signal has an amplitude of around 10 to 100 millikelvin square. But if you look at the radio sky, you will see signal at the amplitude of around kelvins, so hundreds to thousands of Kelvin at this frequency. So these are our bright emission from our galaxy. And even if you go to some places where the emissions are less brighter, you will see the emission from other galaxies. So these are called extragalactic point sources. These are also extremely bright sources. So these are all. So the brightness of these signals, the foreground signal, is around 4 or 5 orders of magnitude brighter than the 20 centimeter signal, and that is the main reason why 20 centimeter signal has not been observed yet. There are a few good things. The foreground signal are smooth in frequency, or expected to be smooth in frequency. So they should lie in the Fourier domain. In the Fourier domain, they should lie at lower k parallel. So something that is smooth, they lies at lower k parallel. And the 20 centimeter signal from epoch of reionization should lie at higher k parallel. But because the instrument also works in a frequency dependent way, it leads to some leakage of the intrinsic foregrounds and creates a wedge-like feature. So these are all these regions which is not accessible to us. And this window is the only hope where we can try to measure the UR signal. So that's the introduction. I'll now move into the data that I am working with. So I hope this is clear what the goal is. So my goal is to have this radio observations from the MWA to measure the UR power spectrum. And what I expect is to get something like this, where I want to use this kind of region to measure my UR signal, and then use that to tell cosmology or the astrophysics, rich astrophysics of that epoch. So a brief description of the observation. So these are called drift scan observation. What happens is that your telescope remains fixed on Earth, and as the Earth rotates, we observe different parts of the sky. So these are called, this particular mode of operation is called a drift scan observation. So basically, if I plot the sky in this area and deck coordinates, my observation spans. So this for example, central blob is called the response of the instrument. So my instrument is can only see this part of the sky, which is my concern. There are multiple other lines, but you can ignore that. And then as the sky drifts, I observe different parts of the sky, starting from this green star to this green star, So this entire sky is being observed. Each of the observation is called one pointing. And my next few slides will be concerned about only one pointing. Okay. So yeah, so far so good. So this is what we get when we make the measurement of the power spectrum. So this is from actual observations. There is no simulation involved here. So if you make actual observations, you get a power spectrum like this. So what I said earlier is that foregrounds, these high powers are from foregrounds. We expected the foregrounds to remain at low k parallel, but you can see that the foregrounds are leaking periodically to high k parallel. So my wish was to measure the UR signal from this region, but you can see that all of these regions are now contaminated by foregrounds. The goal of this entire 21 centimeter observations is to get this region cleaner by developing methods, by improving your instruments, by modeling the foregrounds, you name it. That is the goal. Now, specific to MWA, why is this periodic kind of feature appears? This is because the MWA has a peculiar kind of uh, pattern in their frequency detection that is called the band pass in radio astronomy. So their band pass has this kind of flagging, periodic kind of flagging. For example, here I've shown these filled regions are unflagged regions. So these data are usable, and these gaps are flagged regions. So these data are not usable. This has to do with their design of the band of their correlator, and this is particularly a particular phase of the MWA. So MWA instrument is also getting upgraded. They're changing their correlator. Very new instrument doesn't have this problem, but before 2025 or 2024 or 5, this pattern was there. And these are the kind of measurements all the papers have reported. So basically, it seems that measuring the EOR signal from this kind of instrument is useless. But I'll show you that we are able to produce some results like this by doing some kind of exercise in this region, cutting something and then filtering the foregrounds, and we are able to get this kind of clean region. Why this is clean, I'll explain it a little bit more. But if you can compare this to this, so this is the amplitude has gone down to around 10 to the power 7 millikelvin square. It's still higher than the 21 centimeter signal, of course, but this is much improved than this. How we have achieved this kind of results is what I shall explain in the next few slides. This is possibly the only slide with details mathematics, but you don't have to go into these details. I will just briefly tell the crux of this. So these are my measurements. These are called visibilities in radio interferometer. So we cross correlate visibilities at two different frequency to get this covariance of the signal. And this is an important thing. We assume that the signal is ergodic. So the two different frequency channels, so the signal along the line of sight is homogeneous. This is what we assume, which is mostly true for the EOR signal. Why do you do it? Because the Fourier transform of this quantity directly gives me the power spectrum. So even if there are missing frequencies, I can have a pair of frequency that has an estimate. So basically, I don't have any missing delta nu. So my Fourier transform shouldn't have those kind of periodic ripples of the foregrounds that we earlier had. So that is the main idea. There are a series of papers on this developed over 20 years. So yeah, so this one slide is for all of this. And we have tried this method on simulated data, and that shows that even if the data had the same flagging, there is no, you can recover the EOR signal. Basically, this is what the signal, the slide is showing. But when we apply this to actual data, we see that these kind of ripples again come into the data. So these ripples are not completely gone. So this shows only one of the slices along this. One of the slices along this is shows the same ripples still coming up, although the amplitude have gone down significantly. So why does this ripple come? So and the ripples are problematic because these are foregrounds basically. So in the presence of foregrounds, you cannot see the 20 centimeter signal. So you have to make methods so that these ripples go away, and you can see the noise and then add more data to get the signal. And so we investigated a lot to understand that the actual reason is again the foregrounds. So the idea that your 2-point correlation remains unaffected. So the idea of that the 2-point correlation works in the presence of missing channels holds only when the signal is stationary. That is they're statistically homogeneous along the line of sight, which the foregrounds are not. So foregrounds are like power law. So at what two frequency I'm making the estimates, that matters. It doesn't matter for your signal, but it matters for the foregrounds. For example, so to summarize this, for a non-stationary signal, the two frequency pair with the same separation length, for example, this separation length and this separation length, they are not identical, but they are identical for your signal. And so in the presence of foreground, this method doesn't work. So we proposed a new method, which is called filtering method, where we first filter out the smooth frequency dependent term from the data by doing some convolution with a window function. So so basically you take the data, you convolve the data with a window function, and so you get the smooth part. You subtract the smooth part to make the data as noise-like or as ergodic as possible, and then you apply your estimator on this. So because I have filtered out the smooth part, I lose some large scale signal, but my small scale signal where the transient signal lies remains intact. So that's the main idea. And that gives you this kind of power spectrum. So this was the power spectrum before applying this smooth component filtering. And after applying this smooth component filtering, where this is the length scale where the filtering has been applied, you can get a cleaner region to measure the UR signal. If we go into this measurements, we see that these periodic spikes that previously we had are now mitigated significantly, and these are all within the noise level that we can estimate. And if you look at the histogram of those measurements by plotting them against the noise variance, we see a very clean noise-like histogram and roughly consistent with the noise estimates. I mean, for our noise estimate, you expect the sigma mu to be 0 and sigma to be close to 1, which is almost we have. There is a factor of 1.4 difference, and we expect that this is because our understanding or estimate of the noise are not very accurate. So far so good. We have reached the noise floor with this data. Previously, we were foreground dominated. So we have now reached the noise level. And the idea is that you keep on adding more data points so that the noise goes down and you finally able to measure the UR signal. So what we then did is that, so all the power spectrum that I showed you were from only a single pointing. Now the next task is to add up all the measurement from all the pointings to reduce the noise and improve the signal to noise ratio. And we have done that. And this is what we get. So this is not a very clean plot, but I will help you to walk it through. So this shows the measured power spectrum, the upper limit on the power. So we define some quantity that is called the upper limit, which is the measurement plus 2 sigma. So the 20 centimeter signal, if they were above this, we must have detected it. So because we have not detected the 20 centimeter signal, we place an upper limit on the 20 centimeter signal. So the goal is to go as low as possible so that we can detect that signal at some point. So this is where our upper limit sits with roughly 7 hours of data. And you can see that this is much improved than various other measurements where people have used even longer observation time. So this is very interesting in the sense that we have listed very, very low value of the upper limit with only 7 hours of data. This one is the lowest currently observed from the Hera telescope, and this uses 94 nights of data compared to only 10 nights of data that we have, or roughly around 7 hours of data. And if we compare it globally of different upper limits that people have at different redshift, so our upper limits is right around here. So this is at this kind of redshift, this is very low, only above than the Hera, as I said. This is, of course, from much sensitive data. And now, as I promised in the abstract that this is this is not the end, I'll show some new methods which is promising even more, so that we can go even better. We can do even better with the same data. So this is a Bayesian method. So Bayesian smooth component filtering. So why do I need a Bayesian filter? What was the limitations of the previous method? So in the previous method, our small angular scales are unavailable. You can see these foregrounds are still there. These foregrounds, the wedge-like feature, are still there. And we couldn't use this part of the data, this part of the k perpendicular, k parallel modes. We only remain confined to this mode. So these are some information. This small scale information is particularly important for people who are testing dark matter models. So these are very interesting in that sense. So we want to recover this part also. And then if you look very carefully that these spikes are not completely gone, they are there still. For example, this faint streak is still there, and that these are close to the noise level, but still not noisy. So if you add more sensitive data, they pop up. And in our in our analysis, we had to mask out these particular Fourier modes. So these are test traces of the residual foregrounds or systematics. We want to improve on that. And then if we look into the power spectrum as a function of RA, so for example, I have estimated power spectrum from each of the pointing center, then you will see that at some pointing centers, the power is very high. So why is that? We know this, why this is high. So there is a very strong radio source 4NX-A sitting here, and our technique of filtering is not able to remove this kind of very strong signal. So you see a very foreground dominated estimates, whereas in this region, you can see you have hit the noise level. So these two sigma error bars are crossing the floor. So these are good pointings and these are bad pointings, but they are not bad in the sense they're intrinsically bad. They're bad because our technique has failed to remove the foregrounds from them. So I have shown three reasons why you should be aim to go for an improved analysis. So this is this paper has now been accepted in MNRAS. So I have proposed a Bayesian filter that can mitigate this kind of foreground leakage even from strong foregrounds and even in the presence of highly missing channels. So I encourage you to go and look into this paper. I'll just share one plot from the paper. So this is a simulated data. So I have simulated strong foregrounds. Strong foregrounds have this kind of oscillatory features. And this is a similar foreground, but a different realization of the same foregrounds. And I have fitted it with hand-based smoothing. There is this dotted line, I hope you can see. And then there is this Gaussian process-based Bayesian smoothing. So the Bayesian smoother almost fits the data quite well. And you can see the residual here. So this black is the filtered 21 centimeter signal, and the orange is what I get from GP. So they are basically overlapping. So I can recover the UR signal here. But you can see that the hand window is failing at those regions where the foregrounds have strong features. For example, here and here. And these are the residuals from the foregrounds that remain. And these are divided by 300. So these are even 300 times higher. So basically, I'm saying is that the hand-based CF were quite good, but they are not good enough to detect the UR 21 centimeter signal because the signal is very faint. And so we will now use the Bayesian SCF, Bayesian smooth component filtering to go even deeper. So I hope I didn't take more than the time that was allocated to me. So I will summarize. So I presented in my first few slides that the epoch of reionization is a very scientifically rich epoch. It poses several questions, and there are very limited few direct probes. One of the direct probe is the EUR, the 21 centimeter signal from the neutral hydrogen. But the problem is that the foregrounds are too bright to see this very faint signal. A very powerful instrument I am using, that is the MWA, and this MWA is will actually be succeeded by the SKA. So this is a very futuristic instrument. One of the problem it had, because it doesn't have now, but there are lots of data sitting which had this problem, is the periodic gaps in the frequency that leaks the foreground into the UR window that obscures the 21 centimeter signal. The SCF method that I am proposing, it is filtering the smooth component, and then this 2-point correlation width method then takes care of the rest. So that finally gives you noise limited measurements. Now you can keep on adding data points to get tighter upper limits from the same instrument. And at the end of the few slides, I showed why we need to do more improvements, and the Bayesian SCF can do that. We have lots of sensitive MWA data there. Now we will use this new technique to go even deeper and then go closer to detecting the 20 centimeter signal. So in next few years or so, you can expect even tighter constraints on the EOR model, and hopefully we can go on to detect the signal. So thanks very much for paying attention, and I